Maybe? Great. Hi. Oh my gosh. We're in 3 dimensions, and I'm so excited about it. It is so amazing to be back here. I was gutted to have to miss my annual trip to Cluj the last couple years, so excited to be back. My name is Anjana Vakil. You can find me on Twitter at my name, and I would like to talk to y'all today about the art of functional programming. So, yeah, functions! Woo! I think, and I tend to be very loud about the fact that I think functional programming is really beautiful. Not just visually beautiful, as we'll see that it can be today, but a beautiful programming paradigm that is just a really interesting and elegant, I think, way to think about how computer programs can run. And that's because it is really easy to predict what's going to happen in a functional program. That means it's easy to test what's going to happen, and it's easy to debug when something is going wrong. So that's why a lot of programmers find that functional programming is like really lovely, and they find it very easy to fall in love with FP, or functional programming. But I think functional programming can also be pretty easy to fear and be afraid of, because it has this sort of bad but probably well-deserved reputation as being this very kind of elitist, jargon-heavy, obscure, super intense academic field that isn't always seen as very accessible to newcomers. So that's why I make it my personal mission to try to show folks that functional programming is not as scary as it sometimes seems, with all the jargon and the formulas and the mathy notation and blah, blah, blah. I don't know any of that. I don't have a background in CS or in math, and I can understand some basic principles of functional programming, so that means anyone can understand some basic principles of functional programming. So this is what you find me yakking about a lot. For example, if you want to learn more details about kind of the basic principles of functional programming, you can check out a old but still hopefully correct talk about learning functional programming in JavaScript. You can find on YouTube on the JSConf channel. And shameless plug, I also have a course online on the website Front End Masters that's all about getting started with functional programming. So we're not going to be going into like a ton of details about the basics of functional programming, but I just want to recap the most important things. So what is functional programming? Well, functional programming is programming with functions. I'm done. Goodbye. Okay. Yeah, okay. So, all right, yes, it's programming with functions. So what? So it's not just any functions, though. It's programming with pure functions. In JavaScript, for example, the function keyword, or something that we create with an arrow function, doesn't necessarily have to be a pure function. So when we do functional programming, we make sure we enforce more constraints on what we consider a function. It has to be pure. What does that mean? Well, a pure function is something that takes input and returns output. And that is all that it does. That is literally all that it does in the world, is look at its inputs and return some kind of output. So for example, a very simple function maybe gives you the aspect ratio. What do you need to determine the aspect ratio? You need to know the width and the height. So those both need to be inputs. And then the output is just the value of their ratio. Super simple, boring function. But this is the idea. There's only inputs in, there's only outputs out. So that means a pure function is deterministic, meaning every time you run it with the same inputs, you're going to get the same output. It's never going to change based on some other thing, something in the state of the world or the state of the program. These functions, these pure functions, they are stateless. That means they don't have any values changing over time. So whenever you call a pure function, or apply, to use the functional programming word, a pure function with the same inputs, you're gonna get the same output. It's fully deterministic. That's what makes it so nice and predictable and so easy to test, because you just pass in the inputs and see if you get the right outputs. And so this also means that it is a function that is free of doing any side effects. So a side effect is anything the function might do that is not returning its output value. So this could be something that it's doing outside of the program, something else in the world. Like, for example, console logging. Not allowed, because that's not returning a value. That's doing something else. Changing the DOM, touching the DOM. Not allowed, because that's changing something in the world. All a pure function can do is return its output. And similarly, we said that the pure function has to be deterministic, so it's going to be the same every time it runs with the same inputs. That means it also can't look at any other state in the world. Like, for example, reading the value of some attribute on some element, because that could have changed. So that could mean that if you're reading some value from the outside world that's coming in outside of the function's inputs, it might change on you. And then when you call the function again, you get a different value. So side effects are to be avoided in functional programming. So that means you can't do stuff like log, you can't do stuff like touch the DOM, you can't do stuff like set or get attributes from outside of the function. So, like, what can you do, right? How are you supposed to do anything in a world of pure functions where they're not allowed to do anything? All they can do is return values. So this is kind of the next question that I think folks usually get to when they start learning about functional programming. Is like, okay, in an academic theoretical setting, that's all fine and good that we have all pure functions, but I'm trying to do stuff in the real world. So how do I do that? Functional programming can do whatever we need it to do in the real world. There's just a couple of techniques that we maybe need to learn and get used to in order to make that happen. So that's what I want to do today, is take a look at how functional programming works in reality. And in order to do that, we're going to use the example of art. Yay! We're going to make art. Huzzah! Not as beautiful art as what Madalena makes over here, doing the amazing sketch notes, but we're going to make some nice little drawings for ourselves and hopefully learn a couple of things about doing functional programming in the process. All right, you ready? Yeah! Okay, so the first thing we said is that pure functions can't do side effects. No side effects. No logging, no touching the DOM, no taking user input, for example. So what do? How do we handle side effects in pure functional land? Well, we don't. Instead, what we do is we take the side effects that we need and we push them to the outer edge of our program. Sometimes this is called, we make like an imperative shell around our program, and then we keep the inner core of the program pure functional. So we take anything we need to do that involves the rest of the outside world, like doing side effects, logging things, reading global state or program state, touching the DOM, those kind of things. We keep that all on the outermost layer of the program, and we isolate any impurity there, and then we keep the core of the program pure. So this is like one of the strategies we can use. And this is what's going to basically keep the innermost part of our program, the functionality, really the computation, it's going to keep it deterministic, it's going to keep it safe and predictable and easy to debug, etc. And then we'll just isolate anything that's not so safe or not so predictable, that's non-deterministic, out on the very, very outermost edge of the program. So let's take a look at what that might look like if we're trying to draw some art. And that's going to involve, if we want to make some art, we're going to need side effects. We're going to need to touch the DOM if we want to put something on a page. We're going to maybe need some state, because we might need to remember kind of like where we are in the program. And we might need to, for example, take in user input. So any of these things that's non-deterministic is going to stay on the outside. And for now, let's take a look at that most important side effect of getting some art on the page. Okay, so here is something that hopefully is readable. What we have here is the outer shell of a functional program. This is imperative. This is not pure. That's why I named this function impure set SVG contents. So what I have is I have some HTML, I have an SVG element, and what I'm doing in my impure, imperative, not functional function is grabbing that art element from the DOM, and again, that could have changed in the meantime, so this might be different every time we run it, and then we're setting its inner HTML as just a quick and dirty way of getting some content in there. And so this means that this is changing the outside world. So that's why this is impure. But the way I can use this is I can take that impure wrapper and call it on a program that gets my art in a pure functional way based on some parameters that I pass into it. So what we've got now, we've got our impure set SVG contents is our imperative outer shell that does side effects. And then this pure get art, whatever, is going to do some computation that gets us the contents that we need that will be deterministic. With me so far? Sweet. Excellent. Okay, so let's take a look at a few different things that and how they might be handled in functional programming. So one question we might have is, how does functional programming handle repetition? So in functional programs, we don't have state. So we don't have, state means values changing over time. So that means we can't do something like a for loop where we're incrementing I every run of the for loop, for example. So instead of using iteration like we do in imperative land, we use recursion in functional land. And I'm not going to go into too much detail about this because I already did a couple years ago. So I gave a talk here, I don't know, 2018? Yeah, recursion, iteration, and JavaScript, a love story. So if you want to nerd out with me more about recursion versus iteration and how recursion works and what it can do for us in JavaScript, you can check that out on the JSHeroes YouTube channel. Okay, but so let's try to draw a little pattern that lends itself very nicely to recursion. So what I've got here is I want to draw this pattern where essentially I'm starting with a single tile, and I'm then recursively drawing more and more tiles until I reach a certain limiting factor. In this case, a minimum width. So a recursive function has to have two things. It has to have a base case where you do not do recursion, and then it has to have a recursive case where you call the function itself. So what I've got here is a base case where if I am trying to draw a tile that's too small, I'm just going to stop. I'm just going to return just the contents of that tile. But if I'm trying to draw a tile that's bigger, I'm going to recursively rotate and draw a tile in the alternating color. And just do that over and over again with recursive calls to my, in this case, get pattern. And so that's going to take two different colors, and it's basically going to swap them every time it calls itself to get this cool alternating pattern. So if I call it with lime green and Rebecca purple, for example, starting at 100, it's going to pop down to 50 and then pop down to 25 and so on and so forth, rotating the drawing at each step until I get this cool, trippy art pattern. So this is an example of how functional programming can do this type of repetition without using stateful iteration. Cool? Cool? Okay, we're with us, we're together. Yes, excellent, wonderful. All right, now we said that there's no state in functional programming, but if I was trying to draw some art, for example, I might use state. I might, for example, keep track of like where I am in the image and use that to determine the value of something, a color, what have you. So how do we do that in functional land? Well, one thing we can do is pretend that state is actually a piece of data. So what we can do is we can represent everything that we care about in the world and treat it like a piece of data, maybe an object, maybe an array with some values. And then I can have a function which takes that current state and some new input and computes what the new state should be, along with whatever output it maybe needs. Yeah? So what we're going to do then is basically treat our new state as like a new output value that we're going to change based on the values of our inputs. So we stick to our functional principles where we always have everything that we care about, every piece of data that we care about comes in the function inputs, and the only thing we do is return output. So let's take a look at using that in a functional program. Brace yourselves. I think the next slide has like way too much code on it. Nope, okay, not yet. Surprise! So this is going back to our imperative shell functional core. We can keep the notion of values changing in time on the outer imperative shell of our program. And then inside the functional core, again, we have a stateless world. So we're treating that state like it's data inside our functional program. Here's the bunch of code that is terrible. Okay, so what we have here, what I'm trying to do is just draw a basic, like, n by n grid of tiles. Cool? The thing in the bottom right. We're trying to draw an n by n grid. How do we do that? Well, usually we would do like a for loop, like for column index, for blah of row index, and then iterate over all of the columns and the rows, right? That's probably what a lot of us would reach for to do this. Instead, we are going to do it recursively, and we're going to keep track of where we are and how many columns we need to do, how many columns and rows we have left to draw, by keeping track of that as our input parameters. Like, here I have a function getTiles, which is going to take some width and some height that I'm drawing this image in, and it's going to keep track of the number of columns and the number of rows that I'm going to be drawing. It's then going to take in some function, and this is another thing in functional land. We pass around functions like they're data. It's going to take in some function that's going to draw the actual tile, like whatever goes in the square, and any data that that function might need, which is going to be up to the function. So those are the parameters that we have in our getTiles function. So what happens? Well, first of all, that makeTile function and the data that it operates on, it might update that data. It might make some changes to its own state. So we're going to return that as new data along with whatever tile value it's generating. So that's what's happening in our first line up there. Then we have our base case so that we don't recurse infinitely. So if we only have one tile to draw, we only have one column and one row, we're done. We just return the tile. And if we have more than one column or row, we return the tile plus a sort of smaller call to getTiles with a reduced width or a reduced height and a reduced number of columns or rows. So what we're doing is we're passing through that state of like how many tiles do I have left to draw. That thing that we otherwise in imperative world would be tracking with some kind of incremented value in a loop. We're tracking that with the parameters themselves. The state that's passed into the values that are passed into the function mimic state. With me so far? Excellent. Thank you for folks who are nodding. Love ya. All right. And so then what we've got here is a very, very simple, not that exciting tile function, which is just going to return a tile of a certain color. And it's not really returning any different state. It's returning the same data every time it's called. So all of the tiles look the same. But this is the nice thing about functional land is when we call our getTiles function, we don't have to pass in such a basic function. Tried not to use another word there. We can pass in other makeTile functions to do more cool stuff using this recursive tiling getTiles function that we've now come up with. So let's see what else we can do with it. How about we make a checkerboard? So here we've got, we're going to use the same getTiles function, but we're going to create a new makeTile that's called makeCheckerTile. What that's doing is it's tracking a certain number of colors that we want to alternate between as we draw different squares. And it's tracking the index of the color that we're currently on as part of its input parameters, so part of its quote-unquote state that's not really state because it runs the same every time. So what we've got here is every time we run the makeCheckerTile function, we're going to update the color index to rotate through an array of colors. And in this case, if I call it with two colors, it's going to swap them back and forth, back and forth. With me? Excellent. Excellent. Let's make my pants. So I was in Budapest yesterday, or the day before yesterday, and I found these pants, and I don't know where the camera is or if you can see them, but they're basically a checkerboard pattern, but with a little extra fanciness. A designer called Palmetta in Budapest. Very cool. So let's try to make this weird, trippy pattern using just the tools that we have so far, our getTile function and our makeCheckerTile. Cool? All right. bear with me. So what we need is essentially, on the outer edge, I'm going to have a rotate function. I'm not going to show you the details of that. It's basically wrapping this SVG in a group that transforms it. You could be also using CSS or something to do this. And all that's going to do is rotate it 90 degrees to make it diagonal. Okay, so what we're going to do is we're going to make a new tiling function called makeTiledTile that is going to make each tile in our program, in our art, made up of other tiles. Cool? Recursion. So what we've got here, I'm setting a certain parameter for like the split between, we have sort of an instance of like the bigger squares and then an instance of the smaller squares. So the ratio between them is just some parameter I'm calling split, which isn't going to change, so I've just stuck that in the function. We're basically calculating the split width and split height, or as I like to call them, swidth and shite. Sorry, British friends. And what we're going to do is every time we call this function, we're going to not only update the color index, but update the color index based on basically whether we have an odd or even number of squares in our pattern, so that we get alternating based on if somebody calls this with an odd number of squares or an even number of squares. So then what I'm doing is I'm making 4 different tiles by calling my getTiles function. And each of those tiles are, I'm going to call them big for the big squares, narrow for the one that's squished, wide for the one that's squished horizontally, and small for the little bitty one. And what I'm doing is I'm basically just passing in reduced width and height values to each of those calls to getTile using my good old makeCheckerTile that we just saw from the boring checkerboard pattern. So what we've got now is 4 different tiled pieces that we're smushing together into a single tile and updating the state along the way to make sure that we start off on the right color so that we get the alternating pattern. And so once I pass that in with my orange and hot pink colors, I get my pants. Huh? I don't know. I thought it was pretty fun. Alrighty, so how are we doing for time? Let's see. You might be thinking, Anjana, you said this was a talk about generative art. And usually generative art isn't just like a super predictable number of checkerboard patterns or whatever. Usually generative art has some notion of randomness, right? Because we want the computer to draw us some cool new thing every time we run the program. How do we do that in a deterministic world? How do you have randomness, which is by definition non-deterministic, in a world that doesn't have non-determinism? How can we handle randomness in functional programming? Well, we can't. Functional programming does not have randomness. There's no randomness in functional programming, and actually, none of our computers have randomness. But we do have pseudo-randomness. So we can pretend to have randomness by generating a bunch of values that are different and sampling those values to get essentially something that serves as a random value, which we can then use similarly to like a math.random to alter some parameter of our program. So a really great fun friend for this is something called simplex noise. And here we're just using a little utility library that makes a simplex noise field. And we'll show how a simplex noise field is different than a random noise field in a second. But suffice it to say, what this thing does, when I instantiate a simplex noise generator, it's essentially a pseudo-random number generator that takes a certain seed. And so I can pass in a seed to this pseudo-random number generator and always get the same random numbers out based on that seed. So here, what I'm doing is I've got a function that's called impure get noise field. And that's impure because it is using a function that's pulling in some library from the outside world, right? And who knows what happened on NPM yesterday and what this is pulling in. So this is impure, right? But what we've got then is something that starts to function like a pure function. So when I call impure noise field with a seed like hello noise, I get an object, which then I can use a method on this in this library called noise2d, which essentially sets up a two-dimensional grid of values. And then I can sample a value with an xy coordinate, like 50-50, and get back some pseudo-random number. In this library, they're going to be between -1 and 1. But you can scale that to whatever range of values you need. Just multiply it out. So what I've got is an object called noise, which is going to give me some arbitrary value. It's not fully random, but it's arbitrary enough that I can use it to tweak parts of my art. And the cool thing is, this is deterministic because if I call this function with some other input, I'm going to get a different number at that coordinate. If I generate a noise field from a different seed, like other noise here. But if I generate a new noise field from the same seed, I actually get the same values. So I can still test if this is getting the right things. I can still try to debug by using that same seed in a pseudo-random but deterministic way. So what does this generate? Well, if we zoom out on the noise field, it looks like just basically random values. But if I zoom in, this is the cool thing about the simplex noise, is that the values are actually all related to one another. So as I zoom in on the noise field, I get this kind of nice smooth variation, which can be really cool for art. Because instead of just getting totally unrelated random values, I can have sort of nice smooth patterns throughout my art. So let's try to use it in our tiling code. So here I've got a function called makeRandomTile, which is going to take a few different colors and like give me a colored tile, just a square, in like a random one of those 3 colors, or however many colors I give it. So what I'm doing is I'm basically sampling the noise field with some coordinate that I'm tracking by tracking the index or a value resembling the index of the square that I'm currently drawing, the tile that I'm currently drawing, which again, we're representing state as data, so I'm passing in that tile index as part of the data that goes into my function here. And then each time I return my new state, my new data, I'm going to increment that tile index. And similarly, I'm going to change maybe the color index to be based on a random, pseudo-random value from my noise field at this tile's index. With me? Ish? Okay, cool. So what I get then is this kind of like noisy pattern of just sort of random different colors of tiles. All right, cool, but what else can we do to make this perhaps even more arty? Well, how about we use that to vary a particular graphic? And then we can create this cool kind of mod pattern that has this sort of random element to it, where let's make these clock tiles, I'll call them. This is essentially, we're drawing different circles, and they have a little hand, and we're rotating that hand randomly for each tile. So what we've got is a make clock tile, which again is going to use that noise field as part of its data that it takes in. And it's going to use the noise at a particular spot, wherever this, based on this tile's index, in order to determine the degree to which I should rotate left or right this clock hand. So this gives me a nice sort of organic looking variation. And I could also combine that, for example, with the same alternation, which is not random, but the same alternation that we used in the checkerboard, essentially, to vary the color of the tiles as well. And so now we start to get like some cool mod patterns going. I don't know that I'd print it and put it on my wall, but I still feel pretty good about it because it looks random to me, a human, but it's all pure functions. It's all predictable. It's all deterministic. Okay, I'm just about out of time, which is good because we have just made a bunch of art in a half an hour or so. We talked about side effects. We talked about repetition through recursion. We talked about modeling state as data. And we talked about randomness, which again, in computers is never really random. And in functional land, we can do a lot with by generating at the imperative outer core a random collection of numbers, in this case a field, a 2D field of values, which I can then use to get some variation in my pattern. So look at all the art we made. And the nice part was we got to reuse those functions over and over again. This is the nice modularity of functional programming. So this has been a little journey into the art of functional programming, pun very much intended. But hopefully this has helped us figure out how we can actually do some real-world things and still take the advantage of the nice predictability that the deterministic, pure functional world gives us. So thank you so much. I'm Anjana Vakil on Twitter. I'm going to try to publish some of the code behind these drawings on my observable site, observablehq.com. It's not up yet, but stay tuned in case you want to play around and make your own little tiling functions and so on. And yeah, I just want to give a huge thank you to the organizing team for having me and for putting this all together and for getting us in 3 dimensions again. Thank you so much, everybody.